Hi guys, my name is Peter C. Doppler Jr., mathematics instructor at the University of Liberia and your math tutor. So in my today's lecture, I'm going to be discussing what is a derivative. What do we call derivative? How do we find derivative of functions? So that's exactly what we want to look at right now. So to start with, we have few hints to the definition of derivative. One, we said a derivative is simply a measure of rate of change. So when we are talking about derivative, we are basically referring to how things are changing. How things are changing, right? How one variable changes with respect to another variable, how one variable changes with respect to several other variables, and just about rate of change. So we also said that it is a function, derivative is a function, that tells you the slope of the line that is tangent to a curve. So the derivative tells you the slope of a line that is tangent to a curve at any given point in time. And it gives you the rate of change at any instant or simply the instantaneous rate of change. Now let's find out the proper definition of derivative with the help of limit. And after we found that, we're going to find a suitable formula that we will use later in finding the derivative of functions. Now consider the below diagrams. I arbitrarily selected or I drew randomly this curve. Now, this curve that you see, we can indicate several points on this curve. Several points can be drawn from this curve. Infinitely many points, in fact, can be drawn on this curve. Now, the line that runs through each point, that line is referred to as a tangent line. So when a line runs through a single point, that line is referred to as a tangent line. When a line runs through 2 points on a curve, it is called a secant line, but when it runs through 1 point, it's called a tangent line. Now, so all of these lines, these are lines that run through a single point on the curve. Now, it schemes the curve, right? So it does not touch more than 1 point on a curve. No, it touches a single point on the curve. So there are many tangent lines that can be drawn on a curve. Remember, we said it is a function. The derivative is a function that tells you the slope of the line. So the slope of these lines that are tangent to the curve. So then, if the derivative is a function that tells you the slope of a line that is tangent to the curve, how then do we find the slope of these lines that are tangent to this curve? How do we find the slope of those lines? We are dealing with curve, and these lines, they are running through single point. Each of them is running through a single point on the curve. They are not running through more than 1 point. And we know that to easily find the slope of a line, we need 2 points. So if we have 2 points, we can be able to find the slope of this line, and that value that we're going to get is going to be the slope for every other point, set of points on this particular line. But this case is different. So now what we did in this second diagram, we took a kind of sketch. So we took a sketch of this particular curve and insert it right here. So we're going to use what we know to be able to derive a kind of suitable formula to find the derivative of a function using the limit process. So what do we know? We know that if we have 2 points on a line, we can be able to find the slope. And we know that on a curve, if we select 2 points, and run a line through those 2 points, it means we've gotten a secant line. So what we're going to do is that we're going to use a secant line to approximate the slope of a tangent line, and then later find the exact slope of the tangent line with what we've already gotten. So let's get started. Now we have this diagram. So let's select the first point. Say we have the first point right here. And we call this point X, this X. And then say we have another point right here. Now, since from this X to this point, since there is a change in the X on the X axis, we can name this whole portion some H. So this change, we call this change H. So it means this H plus this X will now give us X plus H. So it means from this origin to this point now is X plus H. So on the Y axis, we have f of x, because if you take x and you put it in the function, you have f of x, right? So for this function now, the independent variable is x. But for this one, excuse me if my lines are not straight, if my sketch not straight, please. So for this one now, we have the independent variable to be x plus h, right? So now let's go ahead now. Now, this is what we need to know. We know that our target is to find the slope of a line that runs through this point, this single point. That's the slope we are wishing to find. So since we don't know that slope for now, we want to find the slope that runs through this point that is up here, and this point that is down here. And this line we've just drawn is referred to as the secant line. And remember, at this particular point, we have x, comma, f of x. And then at this point, we have x plus h, comma, f of x plus h. So those are the two points that we've selected. Now, our target now is to first determine the slope of the secant line. So we know that slope is equal to ras or over run. That's the definition of slope. Meaning, if there is a ras and there is a run, then we will have a slope. So if there is a ras, it means that there is a change in y value. So there is change in y. If there is a run, it means there is a change also in the x value. So we have change in x. Also, if there is a change in y, that is, if there is a ras, it means we will have a higher y, which is y2, and a lower y. So we can say y2 minus y1. Likewise, with the one down here, we can say x2 minus x1. Right? So now let's go ahead. Since we are now finding the slope of the secant line, we now calculate the slope of the secant line. So our y2 now becomes this. So it's f of x plus h minus our y1 now is just f of x, all divided by our x2, the second value, x plus h minus our x1, the first value, x. So we clearly see that x and x can go out. So the slope of the secant line now is equal to f of x plus h minus f of x all over h. So now this is the slope of the secant line that we've just found. But our concern or our target is not to find the slope of a secant line. Our major target is to find the slope of the tangent line, which of course is the derivative. So to do that, we notice that the line that we want to find the slope of, the line is right here. This is the line. This is the line that we want to find the slope of, right? But this secant line that is here like this, what if this change in h that we let's say this change in x that we call the h, what if we compress this h? What if we bring this h closer and closer till it reaches at x? That is, what if we consider h to be getting closer and closer to 0? What's going to happen? So as h gets closer and closer to 0, we're going to leave the approximated slope for tangent line and arrive at the exact slope of the tangent line. Because the tangent line is right here. It's just like taking this line that is here, this line, this blue line, and bringing this blue line down here like this. It's just like you want to bring this blue line down. That is, you're reducing the h space, this space. You want to compress it as you bring it closer and closer and closer to x. H will be approaching 0. So assuming that from this point to this point was 10. When you take this point from here and bring it right there, it reduces. You take it from here and bring it here, it reduces. You take it from here and bring it here, it reduces. So we can consider as h gets closer and closer to 0, we're going to determine the slope of the tangent line. So from that definition or from that analysis, we can conclude that if we take the limit of the secant line as h gets closer and closer to 0, we will arrive at the slope of the tangent line. So thus, we have the derivative would now be equals, because remember we told you the slope of the tangent line is called the derivative. The derivative, which is f prime, would now be the limit. What is the slope of the secant line? F of x plus h minus f of x divided by h as h gets closer and closer to 0. So this is the definition of the derivative. This is what we refer to as the first principle of derivative. So this is the first principle of derivative. So we're going to use this first principle or this definition of derivative to determine the derivative of several other functions in our next videos. So thanks ever so much for watching. Please subscribe to my YouTube channel on YouTube. The name is Peter C. Dugbo Jr. Please subscribe. Thank you very much. See you next time.